Welcome to the deep dive. Today, we're going underground, literally to explore the world of rock mechanics. I know it doesn't exactly sound like a thriller,
Right.
but trust me, this field is way more crucial and interesting than you might think, especially when it comes to oil and gas engineering.
Yeah.
We've got a textbook here, Foundations of Rock Mechanics in Oil and Gas Engineering, ready to guide us. So buckle up, because we're about to unearth some surprising facts about what's happening beneath our feet and how it impacts our everyday lives.
You know, it's true. This field often gets overlooked, but it really is the foundation for so many industries,
Okay.
from oil and gas to mining,
Yeah.
even major construction projects like tunnels and dams.
Okay. I'm already intrigued. You're telling me that understanding rocks is as important as understanding steel and concrete when building a skyscraper.
Absolutely. And in oil and gas, it's becoming even more critical as we push the limits of extraction.
Okay.
Think deeper drilling,
Yeah.
horizontal wells, and of course, hydraulic fracturing. These advancements all demand a deeper understanding of how rocks behave under pressure, especially the immense pressures found deep underground.
So it's not just about digging a hole anymore. It's about navigating a complex hidden world with forces we can't see.
Precisely. And here's the thing. Rocks are far more complex than most people realize. They're not like manufactured materials.
Right.
They're unpredictable, and their behavior can change depending on various factors.
Like what? Give me an example.
We'll take something called the size effect.
Okay.
It means the strength of a rock can actually vary based on the size of the sample you're testing.
Wow.
A small piece might be stronger than a larger one from the same formation. That's something you wouldn't see with steel or concrete.
That's wild. It seems counterintuitive. So you're telling me we can't just assume all rocks from a specific area will behave the same way?
Exactly. And then there's the issue of tensile strength.
Okay.
Rocks are great at withstanding compression. You can squeeze them pretty hard. But try pulling them apart, and they're much weaker. It's almost like they're a non-tensile material.
Okay, so how does that translate to real-world challenges in oil and gas?
Imagine you're drilling a borehole. You're essentially creating a void in the ground, disrupting the natural stress balance in the surrounding rock. If the forces around that borehole create too much tension, you risk fracturing the rock formation.
And that could lead to leaks, right? Or even those dangerous blowouts we hear about in the news.
Exactly. And here's another wrinkle.
Okay.
Groundwater. It plays a surprisingly massive role in rock mechanics and wellbore stability.
Right, water. We don't often think about how much is down there, but how does it affect things?
Well, imagine rocks as a giant sponge. They're full of tiny pores, and those pores often contain water. This water actually weakens the rock, making it more susceptible to problems.
Like what kind of problems?
Think about a phenomenon called spalling. This is where chunks of rock break off from the borehole wall.
Yeah.
Due to stress in the presence of water, you end up with falling blocks, obstructing the wellbore, potentially trapping your expensive drilling equipment.
I'm starting to see how drilling a well is like navigating a minefield.
It is. And remember how we talked about water injection being used to boost oil production?
Right.
Well, that can cause its own set of rock mechanics. Headaches, like sand production.
Sand! Isn't that just well everywhere?
It is. But here's the thing. When sand grains start flowing into the wellbore, along with the oil and gas, it can cause serious damage. Eroded equipment, clogged pipelines, reduced oil output. It's a real headache for the industry.
So it's not just sand. It's a sign that something's gone wrong with the balance of forces in the rock formation.
Exactly. And that's where rock mechanics comes in. Understanding the stresses that lead to sand production is key to preventing it, or at least mitigating its impact.
It seems like every step of the oil and gas process involves these invisible forces acting on the rocks. Makes you appreciate how complex this all really is.
It is. And to really grasp the challenges, we need to delve into the concept of stress itself.
Okay.
How it affects rocks deep underground, and how it changes when we drill into those formations.
Okay, I'm all ears. Let's talk about stress.
Imagine rocks buried deep underground. They're constantly being squeezed from all sides by various forces. You've got the weight of all the rock layers above pressing down due to gravity. That's called overburden pressure.
Okay, so it's like being at the bottom of a giant rock pile.
Exactly. And then you've got horizontal stresses caused by tectonic forces.
Right.
Those massive plates of the Earth's crust pushing and pulling against each other.
Wow, so it's not just gravity, it's the entire planet squeezing these rocks.
Right. And to make things even more complicated, there can be local stresses caused by faults, folds, and other geological features.
That's a lot for a rock to handle.
It is. And this brings us to a crucial concept, principal stresses. These are the three main stresses acting on a rock at any given point,
Okay.
like a three-way tug of war. Their orientation and magnitude determine how the rock will behave, and critically, how it will fracture.
So if I'm picturing this right, it's like each point in the rock is experiencing this invisible push and pull from these three main forces.
Precisely. Now imagine drilling a borehole into this already stressed environment. You're essentially poking a hole in a pressure cooker, and that creates a complex redistribution of stress around the borehole.
Which can lead to all those wellbore instability issues we talked about earlier, like collapse or fracturing.
Exactly. And the type of geological formation you're drilling through, whether it's a high-pressure zone, a weak layer prone to collapse, or a fracture zone, each presents its own set of rock mechanics challenges.
So it's not just about knowing how to drill, it's about understanding the specific rock formations and predicting how they'll react to the drilling process.
Precisely. And that's where the expertise of rock mechanics engineers comes in. They use their knowledge to select the right drilling techniques, design the wellbore appropriately, and manage the drilling fluids to maintain stability and prevent those costly and potentially dangerous complications.
It's amazing how much science and engineering goes into something we usually take for granted, filling up our gas tanks or turning on the lights.
You're absolutely right. And we haven't even touched on hydraulic fracturing yet. That's a whole other deep dive into the world of controlled rock breaking.
That's a topic for another time, but I'm already hooked. Who knew rocks could be so fascinating? All right, we've talked about the natural stresses rocks face deep underground and how drilling can disrupt that balance. But I'm really curious about hydraulic fracturing, or fracking as it's commonly known. It seems like everyone has an opinion on it, but I bet most people, myself included, don't really understand the mechanics of it.
You're right, it's a topic that often sparks heated debates. But from a purely scientific perspective, hydraulic fracturing is a fascinating application of rock mechanics.
So let's leave the politics aside and focus on the science. Can you break down how it actually works?
Essentially, it involves pumping fluid down the wellbore at extremely high pressure, high enough to crack the surrounding rock formation. This fluid is usually a mixture of water, sand, and some chemical additives.
So you're deliberately creating fractures in the rock.
Exactly. And those fractures create pathways for the trapped oil and gas to flow more easily into the wellbore, increasing production. It's like creating a network of tiny highways for the hydrocarbons to escape.
That makes sense. But I'm guessing it's not as simple as just pumping in a bunch of fluid and hoping for the best. Where does the rock mechanics expertise come in?
It's crucial at every stage of the process. First, we need to understand the existing stress field in the rock. Remember those principal stresses we talked about earlier? By knowing their orientation and magnitude, engineers can predict how the fractures will propagate, which direction they'll grow in, and how far they'll extend.
So it's not random, you're actually controlling where those fractures go.
Exactly. The goal is to create fractures that will maximize contact with the oil or gas-bearing zones while minimizing any risks.
And what are some of those risks? I know there's been a lot of concern about fracking causing earthquakes.
That's a valid concern, and it's something that researchers are actively studying. While it's true that fracking can induce seismic activity, the vast majority of these events are very minor, often too small to be felt at the surface.
Okay, that's somewhat reassuring. But I also know there are concerns about groundwater contamination from fracking fluids.
You're right, that's another important issue. However, our focus here is on the mechanics of the process itself, based on the rock mechanics principles we're exploring in our textbook.
Understood. We're sticking to the science of how rocks behave under pressure, not the broader political or environmental debates.
Precisely. And what's fascinating from a rock mechanics perspective is that we're essentially using controlled rock breaking to enhance energy production. It's a powerful tool. But as we've seen with things like sand production, rocks can also break in ways we don't want them to.
That's a great point. It reminds us that we're dealing with incredibly powerful forces deep underground, and we need to understand them thoroughly to avoid unintended consequences.
Exactly. And speaking of unintended consequences, let's revisit sand production. We touched on it earlier, but I think it's worth diving a bit deeper into the mechanics of why it happens.
Yes, please. You mentioned that water injection can trigger it, but I'm still not clear on why those sand grains decide to break free and flow into the wellbore.
Think of it like this. Imagine a microscopic tug-of-war happening within the rock formation. On one side, you have forces trying to hold those sand grains in place.
And what are those holding forces?
Things like cementation. That's the natural glue that binds the grains together.
Yeah.
And then you've got pore pressure, the pressure exerted by the fluids within the rock's tiny pores.
So cementation and pore pressure are teams stay put.
Right. But on the other side of this tug of war, you have the force exerted by the flowing fluids, the oil, gas, and the injected water. They're all trying to drag those sand grains along with them into the wellbore.
So when those dragging forces overcome the holding forces,
You get sand production. The sand grains break free and start flowing, leading to all those problems we talked about. Erosion, clogging, reduced production.
it's amazing how these tiny particles, sand grains, can create such massive challenges for the oil and gas industry.
It is, and this is where rock mechanics really shines. By understanding the factors that influence sand production, engineers can take steps to predict and manage it.
What kind of factors are we talking about?
Things like the strength of the rock itself, the pressure differentials within the reservoir, and the properties of the fluids being produced.
So it's about analyzing all these variables to figure out if a particular well is at risk of sand production.
Exactly. And with that knowledge, engineers can implement sand control measures, like installing special screens or gravel packs to keep the sand out of the wellbore. They can also adjust production strategies to minimize the dragging forces that trigger sand production.
It's like a delicate balancing act, trying to extract the oil and gas without upsetting the forces within the rock formation.
Precisely. It's a constant interplay between understanding the natural rock mechanics and applying engineering solutions to manage those forces.
This is all incredibly fascinating, but I have to ask, how do we actually get this information about rocks? I mean, we can't exactly climb down into a wellbore and take measurements.
You're right, it's not that simple. We need ways to study rocks up close and personal, and that's where laboratory experiments come in.
I've heard about these rock mechanics labs where they basically torture rocks to see how they behave. Tell me more about that.
It's not quite torture, but we do put them through some rigorous testing. Imagine a rock being put through a workout routine designed to reveal its strength and deformation characteristics.
Okay, I'm picturing a tiny rock gym with weights and treadmills.
Not quite, but we do have specialized equipment that allows us to apply different types of stress to rock samples. We can simulate the conditions they experience deep underground, but in a controlled environment where we can carefully measure their response.
So what kind of tests do you run on these rocks?
One common test is the uniaxial compression test. We take a cylindrical sample of rock and squeeze it from the top and bottom until it fails. This tells us the rock's compressive strength, how much squeezing it can take before it breaks.
That sounds pretty straightforward. What other tests are there?
We also have tensile strength tests, where we literally pull the rock apart to see how much tension it can withstand before fracturing.
I'm cringing just thinking about it.
And then there are triaxial tests. These are more sophisticated because they allow us to simulate the complex stress states found deep underground. The rock sample is confined in a chamber and subjected to pressure from all sides, while also being squeezed axially.
Wow, that's a serious pressure cooker. But what do you learn from putting these rocks through such intense tests?
These experiments give us crucial data on how different types of rocks behave under stress. We can determine their strength, their elastic modulus, which tells us how much they deform under load, and their Poisson's ratio, which describes how their shape changes when squeezed.
So you're basically creating a rock profile that helps you predict how that specific type of rock will behave in the real world, miles underground.
Exactly. And this lab data is just one piece of the puzzle. We also use information from well logs. Those detailed measurements taken during drilling and production data like flow rates and pressures to get a comprehensive picture of the reservoir.
So it's a combination of lab experiments, real-world data from the well, and then what? How do you put all this information together?
That's where the power of computer modeling comes in. We can take all this data, the rock properties, the stresses, the fluid behavior, and feed it into sophisticated numerical models and simulations.
This is where things get really high-tech, right?
Absolutely. These models allow us to visualize what's happening deep underground, to predict how the reservoir will respond to different production scenarios. We can test different drilling and completion strategies, assess the risk of sand production, and optimize everything to maximize recovery while minimizing risk.
So it's a data-driven approach, but it's still reliant on that fundamental understanding of rock mechanics.
Exactly. The models are only as good as the data we put into them. And the data is only meaningful if we understand the underlying principles of how rocks behave.
It's like a marriage of science and engineering, using cutting-edge technology to make sense of the ancient forces at play beneath our feet.
I like that analogy. And it's a field that's constantly evolving as we push the boundaries of oil and gas exploration and production, constantly seeking new ways to do it more efficiently and with less environmental impact.
That brings up a question that's been on my mind. What's the future of rock mechanics? I mean, we're talking about rocks which have been around for millions of years. What more can we possibly learn?
That's a great question. And it leads us to a thought-provoking point. Rock mechanics isn't just about oil and gas. It has the potential to play a crucial role in other areas of energy and environmental science.
Okay, you've piqued my curiosity. What else can rock mechanics help us with besides oil and gas?
Well, consider geothermal energy, tapping into the Earth's internal heat as a renewable energy source. It sounds futuristic, but it relies heavily on, you guess it, rock mechanics.
I can see the connection. We're still dealing with deep underground environments, heat pressure.
Exactly. To harness geothermal energy effectively, we need to understand how rocks conduct heat at different depths, how they fracture at hot temperatures, and how to create pathways for those superheated fluids to circulate and bring that heat to the surface.
So the same principles we use to extract oil and gas can help us tap into a clean, renewable source of energy. That's pretty cool.
It is. And it goes beyond that. Think about carbon capture and storage, or CCS, the idea of capturing carbon dioxide emissions and storing them safely underground.
Yeah, I've heard about that. But how does rock mechanics fit into that picture?
It's absolutely essential. We need to ensure that the rocks we choose for storage can hold that CO2 for thousands of years without leaking. That means understanding the rock's porosity, its permeability, and its long-term chemical stability.
So we need to be sure those rocks won't corrode or fracture over time, allowing the CO2 to escape back into the atmosphere.
Precisely. We also need to understand how injecting large volumes of CO2 will affect the stresses and pressures within the rock formation. Remember, we're altering the natural equilibrium, and that could have unintended consequences.
Like triggering earthquakes or creating pathways for the CO2 to migrate to unwanted places.
Exactly. It's a complex challenge, and rock mechanics is at the forefront of finding safe and effective solutions for long-term carbon storage.
It seems like rock mechanics is poised to play a bigger role than ever, not just in meeting our energy needs, but also in addressing climate change.
It is. And that raises an important question for the future. Could a deeper understanding of rock behavior lead to more efficient and environmentally responsible oil and gas production as well?
That's a great point. Instead of just brute forcing our way through the rocks, maybe we can learn to work with them, to extract resources in a way that minimizes our impact.
Precisely. Imagine using our knowledge of rock mechanics to optimize well placement, to reduce the number of wells needed, to minimize the amount of water and chemicals used in fracking, to develop new techniques that are inherently less disruptive to the rock formations.
It's not just about maximizing production. It's about doing it sustainably with a deeper respect for the forces at play beneath our feet.
Couldn't have said it better myself.
This has been an incredible deep dive. I have to admit, I started out thinking rock mechanics was going to be pretty dry, but you've shown me how crucial, complex, and even exciting it can be. It really is the hidden foundation for so much of what we do.
It's been my pleasure. I always enjoy exploring these connections, showing how seemingly obscure concepts like rock mechanics have real-world implications for all of us.
You've definitely succeeded. I feel like I've gained a whole new appreciation for the rocks beneath our feet. And who knows, maybe this deep dive will inspire some of our listeners to explore the world of rock mechanics further. We'll be sure to include some resources in the show notes for those who are interested.
Excellent. And for everyone who joined us on this journey underground, I'll leave you with this final thought. The Earth is a dynamic system constantly evolving with forces shaping and reshaping the rocks beneath our feet. As we continue to explore and interact with this incredible planet, a deeper understanding of rock mechanics will be essential for building a sustainable future.
Well said. Thanks for joining us on the deep dive. Until next time, keep exploring, keep learning, and remember, there's always more to discover even beneath the surface.